Mohammad Faizan. So I'm a research scholar at Indian Institute of Technology, Mandi, from India. So my topic is on gauging energy poverty in India, a multidimensional approach. Access to clean fuels is, it's vital for development and well-being of any household. And if we see in the developing countries like India, they still lag, they lag behind significantly in providing clean energy access to their population, and they have almost 80% of the population in rural India. They don't have access to clean fuels, while as in, it's one fourth, almost 25% of the urban population, which has no access to clean fuels. So they are dependent on biomass for their cooking and all. The deprivation, of these clean and modern energy services makes it difficult, for their population to improve their well-being, and it keeps them away from the opportunities which will be beneficial for their development. So in these countries, most of the population, they are dependent on solid fuel, like firewood, charcoal, animal waste for their daily cooking and lighting and other space heating these uses. So globally, 13% of the population, they lack access to electricity, and 40% of the total population, it's almost uh, more than billion population, which is dependent on traditional biomass for their cooking and cooking needs. So so my this paper is in Indian context. So in India, 51% of the population could not access clean fuel. It's about 2018 study. So which compared to, if we compare to other countries, nearest countries like Pakistan, China, Sri Lanka, and Bangladesh. So 51% of the population in India, they don't have access to clean cooking fuels. So the energy, this situation in developed countries is very different from the developing countries. So where billions of people are dependent, in these developing countries, billions of people are dependent on solid fuels. So this lack of, the lack of access to modern energy services is usually defined as energy poverty. So it's mostly attributed to the people with low income, in energy inefficiency, and no access to, or limited access to modern fuels. So energy poverty as an issue, it got prominence in the 90s, when more than 80% of the population in developing countries, they lacked access, and it was a focus shifted to developing countries. Earlier, it was this energy poverty, that as an issue, it got importance in UK actually, firstly in United Kingdom. So, but in 90s, so the focus shifted to the developing countries. So over the years, the situation has marginally improved, but the lack of access, to clean fuels for cooking and lighting, it still lies in billions. So, however, the notion of energy poverty, it's well accepted around the world. So, but the difference in context of energy poverty still exists in North, which is the developed countries, and global South, the developing countries. So, the definition of energy poverty is vital. So, it's important to understand the scale and nature of the problem and formulate strategies accordingly, and policies to minimize the energy poverty. So here we'll talk about the energy poverty in developed and developing countries. So energy poverty is mostly, known as fuel poverty in developed countries. So UK was one of the first countries to talk about energy poverty in 1970s. So in 1990, with the work of Brenda Boardman, so she brought her book Fuel Poverty from Cold Homes to Affordable Warmth. So in this, this work, that was the roadmap which conceptualized the energy poverty as the inability to afford adequate warmth because of the inefficiency of the home. So later on, it was Hills. They developed low cost, high income approach, so which measures energy poverty and provides major policy implications for most of the European countries. So according to UK fuel strategy of fuel poor household, is one that cannot afford to keep educated warm at a reasonable cost. So the most widely accepted definition of a fuel poor household is one which needs to spend more than 10% of its income on all fuels used and to heat its home to an adequate standard of warmth. So generally, this is defined as 21 degrees Celsius in the living room and 18 degrees Celsius in the other occupied rooms. So the temperature is recommended by the World Health Organization. So over the years, this approach, energy poverty, it got accepted in the other European countries also, like France and Ireland. They use the UK way of measuring energy poverty till 2013. So later it was replaced by the low income high cost. So there are other developed countries like Ireland, Scotland. They are using this 10% poverty line. Similarly, France, where a person is considered fuel poor if he or she encounters particular difficulties in his or her accommodation in terms of energy supply related to the satisfaction of elementary needs. This being due to the inadequacy of financial resources or housing conditions. So on the other hand, if you look into the developing countries, so they have used some other measures, like we can define them into unidimensional measures and the multidimensional measures. So in unidimensional measures, mostly they rely on physical energy or expenditure, looking at the physical energy, what is the need of physical energy for a particular household, or in the rural or in urban areas, how much physical energy we need in the household. So these approach, they put either a single dimension. They are using a single dimension and like energy use and energy access, which was used by the Pythagorean string. So similarly. If we go to unidimensional measures, earlier unidimensional measures like which was given by Bravo and Goldenberg in 1983. So according to the calculations of Krugman and Goldberg, so they say like in the rural areas, the direct energy needs per capita per day varies from 10.7 kilowatts in the hot climate and to the 43 kilowatt hours in the cold climate. And similarly, in urban areas, the energy needs per capita per day varies from 6.87 kilowatt hours hot climate to 18.37 kilowatt hours cold climate. So and similarly, there was another study by Modi, McLeod, and Sajir. So they examined various surveys from around the world, and they estimated 1.61 kilowatts per capita per day as the minimum requirement of energy irrespective of the region. So similarly, there is another unidimensional approach that was by Khandekar and others. So where they determine an energy threshold based on the estimations of energy use, energy consumption. So they define the threshold as the income decile, where the energy consumption increases with the increase in income, and below which a household consumes a bare minimum of energy for basic needs like cooking, lighting, space heating, and should be considered as the energy port below that decile. So similarly, there are some expenditure-based studies, or we can say income-based poverty, energy poverty measures. So, which was like one of them is the Foster. So, which was the fuel poverty line, which estimates the energy, average energy consumption of the household. So, where per capita energy consumption falls within plus or minus 10% of the income poverty line. And in the multi-dimension measures, there are various multi-dimension energy poverty measures like Nussbaumer. So he proposed a multi-dimension energy poverty index based on different indicators of the household energy needs. And similarly, there was correlation sensitive energy poverty index, which was developed by Bench. So where like in this correlation sensitive energy poverty index, they use only a single, they say using different dimensions, but if a person or a household is poor in one dimension, so they say that that household suffers with energy poverty. So and similarly, there were other other measures like energy poverty index, which was developed by Mirza and Sirmai in Pakistan, and there is another thing, total energy excess, which was developed by Practical Action, this NGO. So they consider consider other minimum services, such as cooling, information, and communication, and besides that, earning a living apart from cooking, lighting, and space heating. So they recognize energy needs across home, work, and community, and the emphasis should be on the supply of energy, but not only on the supply of energy, but also the services they provide. So, so the rationale of this study, so the key elements which affect energy poverty in a household, or the household income, or we can say the expenditure of the household, the cost of the fuels, the type of energy consumed by the household, which is affected by energy efficiency of the fuels used. So what kind of fuels they are using? So the efficiency of those fuels, the efficiency of firewood, for example, is very low as compared to other fuels like electricity, which has a better efficiency than other fuels. So these studies, the conduct which were conducted in developing countries, especially on India, so they have not considered all the elements together. So here, all the elements are related to each other, and they affect the consumption of energy and income efficient modern fuels for their daily use. So it becomes inevitable to understand each element which contributes to well-being of the household. So unavailability of efficient energy and technologies for cooking, lighting, and space heating households with inability to pay deny the basic opportunities of health, education, and various other opportunities towards households. So by realizing the importance of these elements, so we created an index to understand the effects of all these elements on the outcome of energy poverty. So energy poverty is a multidimensional like general poverty. Hence, this study has analyzed the multidimensionality of energy poverty by developing the multidimensional scores of the household. So data we have used the National Sample Survey Organization, the 68th round of the household consumer expenditure conducted by the Government of India. So we test the multi-dimensional of energy poverty using that data. So this data is of 2012, 11, 12. This study, this data was collected in 2012-13. So this is the methodology. We have used 5 dimensions: dimension of cooking, lighting, dimension of access to basic energy services, a dimension of consumption of energy, services, and services, dimension of services through household appliances and entertainment, communication. And we have given the weight to each dimension. Cooking was allotted the highest dimension, as cooking is very, cooking fuel. So the deprivation of the deprivation thing for use, like for example, for the cooking dimension, if any household is using using solid fuels, coke, coal, this other than LPG, so they are poor in this dimension. Similarly, for the lighting dimension, if a household is using any other thing except the electricity, so that household will be poor in that dimension. Similarly, for the basic energy services, so if the per capita daily consumption expenditure is less than 0.792, so if that's below that threshold, so that household is poor in that dimension, also. And similarly, the consumption of energy services, for example, if the household is spending more than 10% of their income on energy, accessing the energy, so that household is poor in this dimension. So similarly, if this services too, like for example, the household appliances, if they have electric, fan, AC, fridge, and all other things. So if they have available, they don't have available these services, so that's poor in the household appliances dimension. Similarly, in the entertainment, if they don't have radio and radio, TV, or tape recorders, so they are poor in that dimension. For the communication, similarly, if they don't have mobile phone or landline, so they are poor in this dimension. So these dimensions were accordingly allotted the weight. Cooking was given the highest weight, as cooking fuel is very important. And so from the literature we find out, like cooking fuel, if households are using solid fuel, biomass, or like cow dung and all other things, so that affects the health more than if we than other. So that's why cooking was given the highest weight in this methodology. So this is the mathematical model where a household, first we will define a population where a matrix will be taken for the population, where I are the persons and J are the variables. For example, the dimensions there. So for example, if a person is poor in one dimension, so later on the score of all the dimensions will be calculated, and that will be added in the final. At the final, this this when this addition of all these
You have
these
5 minutes
situations are
more.
okay, okay. So I did all these five these deprivations. So at the end, final cutoff will be used. For here, we have used the final cutoff of zero point 0.4. So if the household falls below the cutoff of zero point 0.4, that they are not poor. But if it goes beyond zero point 0.4, so that household is a poor poor household. So these are the results. So if you look into the results, so here we see the states of Jharkhand, Bihar, Jharkhand, Bihar, Odisha. These are all the states where energy poverty is very high. So we find that these states are they have high energy poverty, and we found like these states are those states where poverty is also high. And if you look into the human development index of these states, so human development index of these states is very low. So so also we find like this is the scores across all the states. So Bihar has the highest MEPI score with 0.74, and followed by other like economically empowered groups like Uttar Pradesh, Chhattisgarh, Jharkhand, Madhya Pradesh, Odisha. So lower and low energy poverty states are Delhi, Chandigarh. These are the all union territories, small states where energy poverty is very less. Similarly, this is the map where we find like lack of access to clean fuel, one of the dimensions. Lack of access to clean fuels for cooking. We find like all these EAG states, monthly power groups. So like Bihar and all, they have highest use of solid biomass, and similarly, if you look at the lack of access to cooking fuel for lighting, so Bihar again that has the highest percentage population, which lacks access to clean fuels like light for like electricity and all. So there is another dimension: lack of lack of access to sufficient energy consumption. We are like again, these are the states. If you look all these states, these are Bihar, Uttar Pradesh, and Madhya Pradesh. They have the highest population, which lack access to minimum energy consumption, which we have taken as 0.79 kilowatt hours per capita per person. So similarly, in figure 6, if you look like this is the consumption of energy, where like more than 10% of the energy more than 10% of energy is spent on accessing energy. So here Odisha, Madhya Pradesh, Punjab, Arunachal Pradesh, Chhattisgarh, Manipur have more than 55% of the population. They consume more than 10% of their expenditure on accessing energy. So this is here trying to compare the different states with the comparison of Human Development Index and the Multidimensional Energy Poverty Index. So here we see like blue line is the MEPI one, and HDI is this orange one. So if you look like there's a inverse relationship between the MEPI and HDI. So if you look like if HDI increases, so MEPI decreases. So accordingly, the highest gap is between in the states of Bihar, Uttar Pradesh, Jharkhand, Chhattisgarh. So they have like high energy poverty, and they have low human development index. So here trying to compare the multidimensional energy poverty with the poverty. So here we see like as poverty increases, so does the multidimensional energy poverty index here. So and the peaks are high for Arunachal Pradesh, Assam, Andhra Pradesh, and similarly it goes high in Jharkhand, and Bihar. Here again, so here we also see like poverty is directly related to the energy poverty index. So here we try to do the sensitivity analysis to understand like if we change the cutoff from 0.4 or we modify the cutoff, so how will it affect the the scores of our scores. So we try to understand, we try to correlate these cutoffs. So first we use the pairwise correlation here to understand. So we change the cutoff from 0.3 between 0.3 and 0.5. So we see like there is high correlation, so that there's not that much of difference or we can see like there is not that much of change in the poverty energy poverty index. So similarly in the Spearman correlation rank correlation in the second table. So here again, like there was not that much of change. So it's almost if you look, so it varies from 0.8 to 0.95 in all these cutoffs. So this was the sensitivity analysis to understand the change in these scores. So so here I'll conclude this study. So we can say accessibility and affordability of clean energy source in any household is essential given the hazards of using biomass on health and environment. So the results from our study, they corroborate that energy poverty is a multidimensional phenomenon. So it needs to be evaluated using a comprehensive approach the multidimensional energy poverty index. So the insights from this study, they can provide policymakers with the possibility of choosing a group of population which needs intervention and be targeted in specific policies. So this index, can also be used to monitor and evaluate public policies regarding energy poverty. And this study lays a basis for another development of energy poverty indicators to improve the access to clean and modern energy services. Thank you.
Okay, thank you, Mohammad. Now it's time for questions. So is there any question from the audience? You can write questions in the chat or raise your hand if you want. Okay, let me, okay. Yeah. Meanwhile, Mohammad, let me ask you a couple of questions.
Sure, sir.
Yes. May you show again your slide number 7, please? Okay, thank you. You claim that of course, and you need the waves needs to add the unity 1, but I'm not sure yet concerning the weights within the column indicators. To the best of my knowledge, the sum is not 1. It is 4, 15 is 55, 20, 75, 15, 9,
55, 75, 90, and then it's 10%. The services through household appliances, and so it's divided into 3. Given each, like if this services is given the 10% of weightage, so that 10% is equally divided into 3 parts, given 3.3% to household appliances, entertainment, and communication. So it's comprised then to 1.
Okay. Another question, and the last one, is concerning the measure, because, for instance, concerning cooking, you claim that model cooking fuel,
yes.
What type of fuel? If it's electricity or whatever, access to electricity, of course, I assume the measure is kilowatts, but you need to homogenize the measure. For instance, you can use tons of oil equivalent, that is in capital letters TOE, in order to have the same measure because you need.
Hello. Yes, sir. Yes, sir. I have used kilowatt hours here, so I have not used the toil ton. Hello.
Yeah.
So I have not. I have for every like this dimension, I have used the kilowatt hours. So I have not used the toil ton equivalent to ton equivalent to oil. So I have not used that. I have used the kilowatt hours for every where. So for the first is the cooking. So here we have it's just a question whether you are using solid fuel or you are using electricity or you are using any other fuel which is not clean. So if you go into the deprivation part, so I have mentioned there. So if any other fuel except the LPG or electricity is used for cooking, so that's they will be poor in that dimension. So there's no question of converting into kilowatt hours. So in the third part, access to basic energy, we have converted into the kilowatt hours. So that's for the third dimension.
Okay, you have another question in the chat by Roula. She claims that if the authors could be kind, what would be the main, in capital letters, main finding of the paper? Your main result, may you highlight the main result of the paper, or in terms of policy reasons, or in terms of an advice to policymakers?
Okay. So actually, this was like here in this paper, we have tried to measure first, trying to understand the energy poverty in developing countries. So so there, like this is a work to understand the energy poverty and trying to measure the energy poverty. So this is definitely, like in the conclusion, like I try to conclude that, like this index, this can be used by the policymakers. They can use this to choose the group of population, like for example, which population or which area, which they lack access, or to clean fuels, or who are depriving in this index. So they can focus on that particular areas instead of focusing on the whole. For example, if I can say for the whole of country, so we don't need to focus on whole of the country here. So like for the policymakers, they can use this index to understand like which group or which area is depriving more. For example, in this study, we find like the states of Bihar, Uttar Pradesh, so they are the economically empowered group. So these states in India, so the policymakers need to focus on these areas more. So like this is how this can help policymakers. So there, in the conclusion, I have tried to said that thing. So I hope this yes.
Okay, there is no time. Thank you, Mohammad. Next paper is measuring energy poverty in Mozambique. Is energy poverty a purely rural phenomenon? And the presenter is Maryème. Is it? Yeah.
Mendita.
It's Mendita.
Oh, Mendita. I'm so sorry, Mendita. Okay. As you know, you have 20 minutes. You can share your presentation. So the floor is yours.
Can you see the presentation?
Yeah.
Very well.
Yes.
Okay. My name is Mendita. Can I start? Hello?
Hello?
Yes, you can start. Go ahead.
Can I start?
Yeah.
My
You
name
can
is
start,
Mendita.
yeah.
My topic is measuring energy poverty in Mozambique. Is energy poverty a purely rural phenomenon? We have an introduction, methods, results, and conclusions. Modern energy services are taken as granted in developed countries, but remain unavailable for many world population in developing countries. In these countries, basic needs such as food, lighting, appliances, water, sanitation, essential healthcare, and communication are challenging. As we can see in this table, Mozambique has great potential of renewable and non-renewable energy sources. It is one of the largest energy producer in Southern African Development Community. However, despite the wealth in energy resources, more than 90% of the energy produced in the country is exported to neighboring countries such as South Africa and Zimbabwe, and to other countries around the world. With a human development index of 0.446, Mozambique is the sixth poorest country in the world. with 67% of its population living in rural areas, of which 78% are women and children under 16 years old. 66% of the active population works in agriculture and forestry, of which 88% are rural women. Almost 7% of the Mozambican population lives without access to electricity. And the majority of the households rely on traditional biomass as the main energy source for cooking. The per capita electricity consumption have been showing a growing trend. However, the average Mozambican per capita electricity consumption of 0.33 megawatt hours still below the average African per capita electricity consumption of 0.6 megawatt hours. Although poverty is mainly related to income and production, the United Nations Sustainable Development Goals highlight that access to modern, reliable, affordable, and clean energy services is the key to fight against the many of today's global development challenges, such as hunger, poverty, inequalities, climate change, and to achieve sustainable development. Therefore, the Mozambican government, recognizing the importance of energy access on achieving sustainable development, adopted the United Nations Sustainable Development Goals in 2015 and committed itself to ensure universal access to electricity by 2030. Therefore, efforts have been undertaken in the country to achieve sustainable development through access to electricity. Projects, investments are made through Ministry of Land, Environment and Rural Development, and they are financed by international agencies such as World Bank. However, all the efforts made on achieving sustainable development are focused on rural development, not paying explicit attention to urban poverty. So having said that, one would ask, is energy poverty a purely rural phenomenon? What is the magnitude and impact of energy poverty what's the magnitude and intensity of energy poverty in the country? So our purpose is to measure the magnitude and intensity of energy poverty, calculating the multidimensional energy poverty index. So to answer our research questions, we'll use the multidimensional energy poverty index approach and the demographic and health surveys data for 7,169 Mozambican households for the year 2015. This is the last available surveys in this topic. The multidimensional energy poverty index approach is composed by 5 dimensions and 6 indicators, which has to do with access to modern fuels for cooking, the exposure to indoor pollution, access to electricity, the ownership of household appliances for entertainment, education, and telecommunication means. And for this methodology, a household is considered energy poor if the combination of the deprivation that it faces exceed a predefined threshold K equal to 0.33. The methodology allows us to compute the headcount ratio, which is the percentage of energy poor households, and the intensity of energy poverty, which is the percentage of energy dimension in which energy poor households have deprivation. Then we'll compute the multidimensional energy poverty index as the product between the headcount ratio and the intensity of energy poverty. Before I present the results of the the magnitude and the intensity of energy poverty in Mozambique. I will present here an overview of the main dimension of energy poverty considered in this study. When speaking about the type of cooking fuels in Mozambique, we can see in this graph that more than 90% of the sampled households rely on traditional biomass, charcoal and wood as the main energy source for cooking. The use of modern fuels such as electricity, natural gas, and coal is incipient and concentrated in urban areas. This may be showing that the use of electricity and natural gas is a financially unavailable option for majority of Mozambican households. We considered that a household is exposed to indoor pollution if it uses traditional biomass as the main energy source and cooks food in the house or in a separate building. So looking to this graph, we can see that almost 50% of the sampled households using traditional biomass as the main energy source for cooking, cooks food in the house or in a separate building. So they are exposed to indoor pollution. The other 51% of the sampled household using traditional biomass as the main energy source for cooking. They also exposed to indoor pollution, but they cooks food outdoor. So the exposure is you can say that it's main. I don't know. Okay. Access to electricity in the country, we can see here in I can say that it's blue dark, that more than 50% of the sampled households lacks access to electricity. At national level, more than 50% of the sampled households lacking access to electricity lives in rural areas. We can see it in the blue, dark blue. And at national level, we can see that 13% of the household lacking access to electricity lives in urban areas, which may be showing that there is urban energy poverty in the country. At the provincial level, we can see that Zambezi and Nampula provinces are the provinces with many households living without access to electricity. There is no many studies about energy poverty in Mozambique. In early assessment of energy poverty in the country using demographic and health surveys data from 2009 found that Mozambique was suffering from acute energy poverty with a multidimensional energy poverty index of 0.9. But Mozambique is no longer suffering from acute index of 0.65. Poorest province followed by Nampula and Cabo Delgado with energy poverty index of 0.79, 0.77, and 0.76 respectively.
The the rest of the audience may hear the presenter.
I think she's having maybe some connection problems then. If you
Yes,
also
I think there
on
are some
energy
connection
poverty
problems.
index
Yeah.
as the head count ratio show us that
Now it's good. No.
she is disconnected. I think she's back. Mendita, can you hear us? Yes, of course, there's always this constraints in virtual conferences. Thank you for your patience while Mendita and Carlos come back. So I think our chair had also some problems. Mendita, can you hear us? Okay.
yes, I can hear
Yeah.
you. Can you
Okay.
hear
Okay.
me?
Okay.
We
Yeah.
can hear you now. Yes.
When did it stop?
Yes. I think in slide 12 it started the connection problems.
Okay, slide 12.
Here.
Okay. I will start in here in slide 12.
I think so. One slide more, please.
I think it was a bit further. Yes.
Slide 11 or 12?
12. Yes. 12.
Okay, I will start in slide 11. It's okay?
It's okay.
Okay. I was saying that we consider that a household is energy poor if it
I know. No.
the
No. No.
combination
No.
of the no.
Sorry. This slide is okay. May you advance? Yes. Again. One more
Yeah.
slide. Yes. One more
Okay.
slide. One more.
Yeah.
One more. One more. Here. Please continue here. I'm going to
Here.
give you
Okay.
I'm going to give you 3 minutes more. Okay.
Okay. I was saying that there is no many studies about energy poverty in Mozambique. So any early assessment of energy poverty in the country using data from 2009 found that Mozambique was suffering from acute energy poverty with a multidimensional energy poverty index of 0.9. Our study showed that Mozambique is no longer suffering from acute energy poverty, having improved to moderate energy poverty with a multidimensional energy poverty index of 0.65. Zambezi is the energy poorest province, followed by Nampula and Cabo Delgado with 0.79, 0.77, 0.76 index of multidimensional energy poverty respectively. The improvement on energy poverty index was, however, accompanied by great inequalities among, as you can see here, with the head count ratio showing that 84% of the energy poor, 84% of the sampled households are energy poor. And they are deprived from 78% of the energy dimensions in consideration in the study. To see if the energy poverty is a purely rural phenomenon, we try to find out where the energy poor household lives. And we found out that in actually 66% of the energy poor households lives in rural areas. However, 34% lives in urban areas, which may be showing that energy poverty is not a purely rural phenomenon. It's also there are households in urban areas with physical access to energy, but cannot afford a minimal quantity of energy to fulfill their very basic needs. So energy poverty is rural and urban phenomenon, and it coexists with income poverty. So the main results we can see is that energy poverty is not a purely rural phenomenon. It's also a urban phenomenon, and it coexists with income poverty, which may be showing that public policies and strategies may be designed targeting low-income households in rural and urban areas to reduce inequalities among the population. And we found diverse landscape of energy poverty in the Mozambican provinces. Can you hear me?
Yeah, yes.
Yes, very well.
Hello?
Yes.
Yes, we
Okay.
can hear you.
We can hear you.
We found diverse. Okay. We found diverse landscape of energy poverty in Mozambican provinces, suggesting that public policies and strategies may be defined at provincial level, not via one umbrella to address energy poverty. Thank you.
Okay, many thanks for your presentation. Now it's time for question. Is there any question from the audience?
There is one question now in the chat.
Yes, you have one question in the chat. The question is the following: is there any relevant policy to alleviate poverty or energy poverty in the country?
Can't hear you. Can you repeat, please?
Yes, of course, yes. The question is the following: is there any relevant policy to alleviate poverty or energy poverty in the country?
Yes, it exists. There are projects, public and private projects that are running in the country to reduce energy poverty through access to electricity. The policy is mainly focused on access to electricity in rural areas.
Okay, thank you for the presentation. We have no time, so let me present the third paper for today. The paper is entitled Distribution Network Planning for Isolated Mini-Grids, a Novel Approach. As you know, you have 20 minutes to present. In addition, 5 minutes for question. And the presenter is Lina?
Yes.
Can you hear me? Okay. So
Yes.
the floor is yours. You may share your presentation.
Okay, can you please confirm you are seeing my presentation now?
Yes, now it's possible to see your presentation. Okay.
Okay, okay. Thank you very much. Good morning, I'm Lina Silva, and I'm going to talk today about RETEP network, that is a distribution network planning tool for isolated mini grids. So, okay, I will start with a quick introduction to the tool. covering which are the main motivations and goals. Then I will explain very briefly how the tool works. Then I will continue with an application in a case study. We will look at a comparative analysis, and I will close with the final remarks. Okay, as some of you remember, in 2015, more than 190 countries adopted the 2030 Agenda for Sustainable Development and the 17th Sustainable Development Goals. As we all know here, lack of energy access is an enormous barrier towards sustainable development. It is an essential component in modern life, and its presence or absence has a strong effect in security, health conditions, education, and economic development. Given the relevance of energy access, a set of initiatives to ensure universal access to sustainable and affordable energy were defined under the Sustainable Development Goal number 7. Since the adoption of the Sustainable Development Goals, the population without electricity has dropped from 1.2 billion to less than 800 million, which is a good process, but there is still a lot of work to be done to ensure everyone has access to affordable and clean electricity. Most of the people lacking electricity access are located in rural regions in developing countries, especially in Africa and South Asia, as you can see in the map here. And approximately 8.7 out of 10 people without electricity is living in rural areas. Since most of these potential end users are located in remote and isolated areas, off-grid electrification using isolated mini-grids is expected to largely contribute to rural electrification. This happens for several reasons, including the quick development of technologies, which is also evident in the reduction of investment costs, and the availability of local renewable energy sources. Among all the components of a mini-grid, we focused on the distribution network, since the investment required to build and maintain the distribution infrastructure has a considerable weight on the total cost of a mini-grid project. The main goal of this work is to develop a tool that is able to provide the user with a preliminary optimized topology of the distribution network for the feasibility analysis of isolated mini-grids. Okay, this tool I'm talking about is named a RETEP network. It is part of a set of planning tools for rural electrification projects that was developed at CEST. This set of tools includes RETEP generation that performs generation capacity planning. It also includes RETEP tariff that compares different tariff models, and RETEP network. RETEP network results in a preliminary topology that minimizes the total length of the network. And I think it is important to mention that before the development of RETEP network, RETEP generation used a simplified method to define the network topology. But yeah, I will talk about the simplified method later. Okay, this is the general structure of the tool. The model's main inputs are the geographical coordinates of the users and the existing geographical restrictions. The restrictions are these elements we want to avoid when planning a network. The main outputs are the total length of the network, the graphical representation of the topology, and some information about the mini-grids and the feeders. As illustrated in this figure, you can see right now the model is composed by a set of 6 interconnected internal modules. The first module is in charge of counting the number of nodes and calculating the number of possible connections between each part of nodes. These connections between nodes are called edges. Next, this module calculates the edges length as the distance between these two nodes that are connected by each edge. And the method used to calculate this length depends on the coordinate system used when importing the coordinates. There are different options available. The output of this model is a list of nodes, edges, and lengths. The next module is the main module of the tool. It addresses the problem of minimizing the length of the distribution network. This is formulated as a minimum spanning tree problem. A minimum spanning tree is a subgraph that connects all the nodes of the main graph with the minimum total length. So to solve this problem, the network implements the Kruskal algorithm. This is preferred over other greedy algorithms like Prim or Dijkstra, mainly due to the possibility to separate the spanning tree into different clusters, which is quite useful when we have geographical restrictions and we may benefit from having different mini grids. To find the optimal spanning tree, the Kruskal algorithm constructs a subgraph by proceeding in the following way. It first sorts all the edges in a non-decreasing order of length. Then it selects the edge with the least length. It checks if by adding this edge to the tree, there is a formation of a cycle. If a cycle is present, then this edge is removed. If not, the edge is included in the subgraph. And then this process is repeated until all the nodes are connected. The output of this model is a list of edges selected and included in the optimal spanning tree, and the total length of the tree, which in this case is the total length of the distribution network. Moving to the restrictions model, the goal of this model is to allow the planner to account for the presence of geographical restrictions or preferences. Such restrictions might affect the topology of the network by requiring, for example, the inclusion of additional feeders or the creation of several mini grids. We have defined 3 types of restrictions. Type 1 includes those restrictions that must be avoided when building a distribution network. In this case, we have white rivers, large lakes, and natural reserves. If we have this kind of restriction, the model excludes any edge that is intersecting the restriction. Type 2 includes those restrictions that may be crossed by the distribution network, but only when it is really necessary. And in this case, we have roads, small rivers, and so on. So to limit the number of intersection points, we have included a penalty factor that is added to these edges crossing this type of restriction. And in this way, we affect the sorting process that is done by the Kruskal algorithm. And then the number of crossing points is minimized. And lastly, restriction type 3 allow the planner to choose a certain preferred path. And this is especially useful in the case of, for example, having a bridge that is crossing a river, and we know that we will prefer to have the network using this bridge. The output of this model is a list of included or excluded edges, and this information is sent back to the main model to recalculate the optimal spanning tree. There are additional models that are a good complement to the main model I just described. For example, with the maximum length model, the planner can exclude edges that have a length greater than a certain limit. And as a result, we may end up with a system with several mini grids. Then the mini grid and feeder model identifies the number of mini grids and feeders, and it classifies the nodes and edges according to the mini grid they belong to. If additional information is provided by, for example, red tape generation, then this model processes this information and provides additional information per mini grid. And once the previous models are executed, Red Tape Network delivers a detailed description of the optimal solution in both a table and a graphical form. And now, to provide you a better overview of the tool, let's look at one case study. For this, an existing village in Ethiopia was chosen. This village is located in the North Gondar zone and has approximately 141 users and 2 main geographical restrictions. I think here it is important to mention that no local assessment was done. This village was chosen mainly due to the presence of these restrictions, which is a good case study for Red Tape Network. In this slide, you can have a look at the selected village. As you can see there. You can see here there is the road, and here we have the river. These are the main restrictions of this case. And yeah, it's important also to mention that electricity access in Ethiopia is a challenge, especially for rural areas where only 10% of the population has access to electricity. Okay, regarding the user coordinates, 141 nodes and its coordinates were identified using Google Maps. In the case of the restrictions, the river was represented by the blue line, while the road corresponds to the red line. There was no available information regarding the categories of the users living in the village. Therefore, the users were categorized as is shown in this table. We assume there are 2 basic schools, 4 markets, and 127 households categorized in 5 different groups depending on their expected energy demand. The study case includes 2 phases. In the first phase, the focus is on the optimization of the distribution network only. And once the distribution network is optimized, the results of a RETEP network are sent to RETEP generation to then calculate the optimal size of the other components of the project, like the PV plant, storage, inverter, and so on, and to calculate some techno-economic indicators. 9 different scenarios were simulated to evaluate the performance of RETEP network, but because we don't have enough time, I will show you just some of them. In this slide, we have on the left scenario 1, which represents an ideal situation, which includes no geographical restrictions, no limitations. And as you can see, RETEP network finds an optimal solution with a single mini-grid. On the right, we have scenario 2, which includes the main restriction for the case study, which is the river that crosses the village. This restriction is categorized as restriction type 1, which means that the restriction should not be crossed. As a result, RETEP network divides the distribution network into mini-grids. Scenario 3A on the left considers the other relevant restriction, that is the road. In this case, the road is categorized as a restriction type 2, which means that the road may be crossed only if needed. To do this, a penalty factor was added to those edges crossing the road. And as you can see, or maybe the figure is too small, but RETEP network crosses the road only in 2 different points, and we have as a result 1 single network. On the right, we have scenario 5, which includes both restrictions, the river and the road, and adopts a penalty factor to minimize the number of road crosses. And on top of that, we have added a maximum length limit, and as a result, the network is divided into 5 small mini-grids. The total, the mini-grid located on the north side of the river fits most of the users, and among the smaller mini-grids, one corresponds to a standalone system, and this one corresponds to a very small mini-grid of 2 users. Okay, I mentioned before that before the development of RETEP network, RETEP generation estimated the total length using a simplified calculation. The simplified calculation here on the right is based on the nearest neighborhood analysis. More specifically, it used the expected mean distance. And the simplified method has some limitations, as it is not compatible with surfaces with irregular shapes. And it assumes that all the nodes are randomly distributed. So in order to evaluate the performance of RETEP network, a comparison with the simplified method was made. This comparison evaluated the total length and the levelized cost of electricity and the net present cost. And then here we have some results. The bar chart here illustrates the total length calculated by the simplified method. The simplified method is the blue bar, and the results from RETEP network that are represented in red. The different shades of red correspond to different microgrids when there are more than a single network in the final solution. The chart clearly shows that the network length calculated by the simplified method is greater than the aggregated length obtained using RETEP network in all the different scenarios. It is essential to highlight that in more realistic scenarios, the defined network length was in all cases shorter than the one calculated by the simplified method, with a length reduction between 18% and 33%. Now, moving to the net present cost, as you can see in the chart, the net present costs are lower when RETEP network is used when compared with the simplified method. Then if we talk again about the realistic scenarios, one may think that, yeah, when we divide the network in different microgrids with multiple generation units, we may end up with solutions that are more expensive than the one when we have one single network and one single generation unit. However, as it is shown in the figure, those scenarios considering multiple mini-grids result are cheaper than some of the other solutions that connect users within a single microgrid. Therefore, RETEP network not only optimizes the total length of the mini-grid, but also allows the user to find more economical solutions when considering multiple configurations and multiple mini-grids. Now let's have a look at the levelized cost of electricity, which represent the cost per kilowatt hour of building and operating the rural electrification projects during the lifetime. The blue line here corresponds to the LCOE obtained when the simplified method was used, while the red bars corresponds to the results when we use RETEP network. The results here are consistent with the one we observed before. And as you can see, the LCOE obtained with the RETEP network is lower in all the cases as the total length, and the net present costs are also reduced. All this, you may think that the savings are small, but the savings generated over 1 year can be quite a significant difference for an end user in an isolated region. Now, I think it is also important to observe how the LCOE changes not only in each scenario, but for every single mini-grid. This is illustrated by the chart on the right. It is important to see that in the majority of cases, the LCOE related to the simplified method is higher. However, there are some cases in which we have some different results. So if we look, for example, at scenario 5, microgrid 4, this LCOE is quite high. And this is because this mini-grid connects only 2 households. Then the investment cost of such network is paid only by these 2 users. If we look at these cases, scenario 6 and scenario 5, the last microgrid, we have also a quite a little bit higher value. And this is because in these cases, we have a system in which we have a standalone configuration, which is more costly per user than the one we can obtain when we have a mini-grid connecting several users. However, it is important to mention that this difference is linked to the cost of generation, given the fact that here we don't have network. And yeah, the first contribution of this work is the construction of a very easy to use tool, which is able to provide the planner with a preliminary optimized topology that is very useful for the feasibility analysis of isolated mini-grids projects. Secondly, this work provides evidence of the relevance of optimizing the length and of the distribution network. And it is important to mention that this is quite relevant when we are trying to minimize total investment costs. Finally, the RETEP network allows the planner to quantify the impact of having alternative network configurations on the energy costs for end users. This was it was evident that having multiple mini-grids may result in considerable savings, but this is not true when the number of users is very small. And in these cases, maybe it is a good option to also consider standalone systems. Yeah, that's all for my side. Thank you very much for your attention.
Okay, thank you, Lina. I'm so sorry, but there is no time. So thank you for the nice presentation. And now it's time to short question from the audience, if any. Okay, I have one short question. It's possible to apply this system or this tool to another parts of the planet, maybe in those countries in Latin America, in the developing stadium?
Yes, this tool can be applied in any isolated area when you can benefit from having mini grids for electrification. It doesn't matter the place. So yeah.
Okay. I think it's a nice tool in order to evaluate how people may access electricity and in general energy. Okay, thank you for the presentation. It's time for the last one paper, shedding light on Moroccan household energy expenditures. The presenter is Maryème Kettani. You have 20 minutes, so you can start.
Okay.
Okay, now
can you see my presentation?
We can see the presentation, yes.
Okay. So thank you. My presentation today will be about energy consumption in the residential sector with specific insights from Morocco. The paper is co-authored by Maria Eugenia Sanin, and this research is a part of a PhD at the Institute for Techno-Economics of Energy Systems and the Center for Economic Policy Studies at every university. So the outline of my presentation is described here. I start first by setting the context and the main objectives of this research. Then I'll give a quick insight of energy in the residential sector in Morocco. And after that, I'll briefly present the data we used in this paper and then move to the three main conclusions or three main results of this paper, which are related to energy consumption, energy poverty, and finally, the potential of solar PV adoption in the residential sector before concluding. The residential sector is a high energy consuming sector, being responsible of about 20% of global energy consumption and weights for about 6% of total CO2 emissions in the world. And most of this energy consumption comes from biofuels and wastes, electricity and gas, but this aggregate percentage show high heterogeneity in the patterns of consumption depending on the regions or the countries. And actually this heterogeneity in consumption may correspond to the observed differences in energy use across households with specifically higher use of more efficient fuels like gas and electricity in higher income countries. And we should notice that this regional disparity concerns also the pace of increase in energy demand. For example, the growth or the average growth of energy demand in non-OECD countries is expected to be 2 times the average growth rate of energy demand in OECD countries by 2040. So there is a strong potential for accelerating energy transition in the residential sector, contributing to reducing CO2 emissions and either at the local or at the global level. So understanding household energy patterns using survey data could provide useful insights for policymakers and decision makers to tailor their energy policies, especially regarding a very low or very high electricity or other fuel consuming households. So the general observation is that in the literature, studies covering household survey data mostly cover developed countries, and there are only very few papers looking at this topic for the MENA regions or in the African context. So which makes this type of research very relevant. So the main objectives of this paper are 3. First, we are interested in the main patterns or main drivers of energy consumption in the residential sector in Morocco, mainly focusing on butane and electricity. In a second time, we're looking at using the same survey data at the main determinants of energy poverty. So in this paper, we retain the definition of Boardman, which qualifies a household as energy poor when he or she spends more than 10% of the income to satisfy energy needs. And finally, we look at the potential of solar PV system, of installing solar PV system in among Moroccan households, and discuss therefore the implications in terms of government expenditures and subsidy redistribution. So just a quick overview of energy consumption in Morocco. The residential sector is the third major consumer of energy behind transport and industry. And data show that there is an increasing trend in this energy demand by households, especially for the two main fuels I mentioned earlier, which are butane and electricity. In one decade, from 2007 to 2017, butane consumption increased by 50%, whereas electricity consumption increased by about 67%. And this transition to modern fuels comes as a replacement of solid biofuels energy consumption, especially for cooking and heating use. So a very specific particularity of MENA countries in general and Morocco in particular is energy subsidies. So in Morocco, butane is subsidized for all households, regardless of their income. Subsidies represent about 2/3 of the real cost of butane. So this is a policy put in place by Morocco to preserve the purchasing power of Moroccan households. Regarding electricity, it's also subsidized for all households. The amount of subsidies depends on the real consumption, the monthly consumption of the households. For example, for lower electricity consuming households who consume less than, for example, 100 kilowatts per month, subsidies to electricity represent about 42% of the real cost of electricity provision in Morocco. Actually, this share decreases for higher income households or higher electricity users. For example, for households consuming more than 500 kilowatts per month, which is the highest class of electricity consumption in Morocco, this subsidy rate is only 8%. So coming to the data, we used in this paper the most recent household survey published in 2018. It concerns data from the period 2013-2014. The survey, the sample includes about 16,000 households, and the database collects different information about households, their dwelling characteristics, and socioeconomic and demographic information. It also contains different information about household expenditures for different types of goods, and especially for energy expenditures. Here in the table, we present the qualitative variables used in this paper. So the sample is dominated by urban households who live in northern regions. These households are mostly headed by males aged between 45 and 70 years old. Most of household heads are active and but they have no education degree. In terms of dwelling ownership, most Moroccan households are owners, live in modern houses, and have access to the electricity network. So here we present the quantitative variables used in our model. In red, we can see the three main dependent variables we're interested in, which are energy expenditures, electricity expenditures, and butane expenditures. In terms of modeling strategy, we decided to use a quantile regression approach Most of paper use an OLS, traditional OLS method, but quantile regression is actually more robust to outliers. There are no constraints on residuals, and especially using quantile regressions, quantile regression allows us to look at the different percentiles of the dependent variables and not only the mean. So it's interesting in terms of results regarding tailoring energy policies. So here I present the main results of the quantile regression model for the three main variables at different percentiles. So I'm not going to go through all the results, but we can see that for electricity and butane, higher income is associated with higher expenditures and higher consumption. Also, higher family size and a great number of rooms is associated with also a higher electricity and butane expenditures. However, contrarily to butane, be it in urban areas and living in the north, in northern regions, is associated with higher electricity consumption but lower butane consumption or expenditures. Also, a very interesting point is that being educated is associated with higher electricity expenditures but lower butane use. So this is a very interesting result, and it can show that policymakers could tailor their policy, especially for this category of households who are well positioned in the society, who live in villas or very big houses, and who have higher income, to incentivize them to reduce their energy consumption. So after that, I said that the second main point we are interested in is energy poverty. So we use a logit model to understand which are the main determinants of energy poverty in Morocco. As I said previously, we use the 10% threshold, Boardman threshold, and the results are presented here. So basically, using the same survey data, we can conclude that about 14% of households in Morocco are considered as energy poor, and this represents about 5 million people in Morocco. So looking at the main determinants of energy poverty, as expected, we can see that households who are more likely to become energy poor are poor households. So economic poverty is really associated to energy poverty and access to modern fuels, and larger family size is also associated to higher probability of becoming energy poor. Also, as shown in the previous presentations in other African countries, households who live in rural areas have higher probabilities to become energy poor, as well as inactive and households with no education level. Okay, so one way to elevate this energy poverty issue is to install solar PV panels. And it's also a way for consumers to reduce their energy bills and prevent from a future increase in electricity prices, in addition to the contribution to the general energy transition in the residential sector. So we decided to look at this potential of solar energy adoption in Morocco. We generally in the literature use the LCOE metric, which has already been explained in the previous presentation. And generally the LCOE of installing solar PV system is compared to the electricity price to see if PV panels achieve grid parity, and to see if it's very worth for the household to install, if it's economically attractive for these households to install PV panels. So this is what we did for the Moroccan case, and we found an LCOE PV of about 17 cents per kilowatt hour. And comparing this figure with the electricity price per class of electricity So can you hear me?
Yes.
Yes,
Sorry.
yeah.
I think there is a little problem.
It was a little problem, only 10 seconds. Continue, please.
So I cannot see if you can hear me yet.
Yes, we can hear you
Yes.
properly.
Okay. So I can continue, therefore. So if we compare the LCOE PV with the electricity price for all electricity classes of consumption, we can see that PV is today competitive only for the very high electricity consumers, which is households that consume more than 500 kilowatt per month. For all the other consumers, PV today is not really competitive. So now that we have the potential of solar PV adoption, we can, using the distribution of electricity expenditures from the survey data, find how much households PV is today competitive. And the result is that about 9,000 households today can install, for them, it's very economically attractive to install a PV system, which brings the minimum installed capacity in the residential sector today in Morocco at about 29 megawatt peak. So knowing that, as I explained in the introduction, for all households, in all electricity consumption classes, there is a electricity subsidy, we can conclude that if all households for which PV is today competitive, meaning households who consume more than 500 kilowatt per month, the government would save a minimum annual amount of about $500,000. So this is not very big, but it could be higher if all households in classes 4 or 3, meaning who consume about 300 to 400 kilowatt per month, install PV system. So to conclude, we found that income and socio-demographic characteristic, as well as dwelling characteristics of households, are significant determinants of electricity and butane expenditures in Morocco. Regarding energy poverty, we found that 14% of households are considered as energy poor using Boardman threshold, and that households who are more likely to become energy poor are households who live in rural areas and who have very low incomes. And finally, regarding the potential of solar PV adoption in Morocco, we find that today PV is only attractive for very high electricity consumers, and that if all these households install their panels, there would be about 29 megawatt peak installed capacity, given some savings in terms of energy subsidies provided by the government of about $500,000. So I finished my presentation. Thank you for your attention.
Okay, thank you for the presentation. We have 2 or 3 minutes to make some questions from the audience.
There is a question in
Yes.
the chat, Carlos.
Yeah. Yes, there is a question. Can you please explain what does the variable region capture? That is,
Okay,
which kind of variables you capture within the whole variable region?
Okay, thank you for your question. Actually, with the variable region, we captured 2 main things. First, we captured the difference in regional economic development. As in Morocco, northern regions concentrate more economic or industrial activities. Also, most of the population is concentrated in the north. And secondly, we also capture information related to temperature, as in the south, we are closer to the desert, so temperatures are very high. So we have both information about climate and socioeconomic development of the regions.
Okay, there is another question in the chat. Can you please explain the logic model? What was your dependent variable? Also, this is another question. If you can please explain quartile regression. So first of all, explain the logic model, in particular, what is the dependent variable? And the second one is, can please explain the quartile regression?
So regarding the logit model, the variable we are interested in is whether the household is energy poor or not. So we calculate this variable energy poor by using the Boardman threshold of 10%. So we have the two variables, which are energy expenditures and total household expenditures, which is used as a proxy of income. So we divide the first by the second to obtain a new variable. And then if the result is higher than 10%, then the household is considered as energy poor. If not, the household is not an energy poor. So this is our variable of interest. Regarding the second question about quantile regression, sorry, I didn't understand. What was the question?
Mohammad, maybe you can
Yes.
clarify. I'll activate your mic, or you can do it also.
Maybe you can switch on your micro. Okay. So okay.
Hello.
So yeah. Yes, Mohammad.
Hi, Maryème. I just wanted to know about the quartile regression. So what is this quartile regression actually? I couldn't understand, like, how did you take the dependent variable, and like what was the dependent variable here? So whether it's like the 25% population, 50% population, 75%, what is like quartile regression here? Just wanted to understand.
Okay. Okay, in the quantile regression, the dependent variable is ordered from the lowest to the highest value. So at the 25, for example, at the 25th percentile, we only consider the first 25% values of our dependent variable, and we do the regression on this subgroup of the households. The aim of the quantile regression is to look at the determinants or the impact of our independent variables on the dependent variable at this first 25% quantile. And we do the same for all.
Sorry to bother. Just wanted to understand, like, what is the dependent variable here? Whether it's the population, whether you are taking the income, or there is any other thing like which is dependent variable here, like the quartile thing. Is it the population or is it the income?
I'm not sure I understood your question, but regarding all the independent variables, we take them as they are in the data set. We do not classify them by percentiles. And for each household, we have a value for income, family size, etc. It's only for the dependent variable. In this case, it's related to energy expenditures, electricity, or butane expenditures that we do this quantile classification, let's say, of our values. It's only related to the dependent variable.
And that's what I wanted to understand. Dependent variable is the energy expenditure.
Yes.
Oh, thank you.
We have three dependent variables: energy, electricity, and butane expenditures that we explain by all the other independent variables like income, family size, number of rooms, etc.
Okay. Again, thank you for coming this session. Thank you, the presenters, for this nice presentation, and nothing else. And enjoy the rest of the conference, because I think there are a lot of interesting questions and issues regarding new researchers and so on. Okay, so thank you for coming.
Thank you, everybody, and thank you, Carlos, for the lead.
Okay.
Have
Bye.
a nice day. See you.
Have a nice day. Bye.
Bye.